Yo, Junkyard Engineering here, and today we're going to be working on a Stewart platform, so stay tuned. In the previous videos, I showed you what forward kinematics is and inverse kinematics is, and how to apply inverse kinematics via geometry through a scalar arm, which is 2-DOF arm. If you haven't watched that video, please watch that video. So typically, what is a Stewart platform? So typically speaking, every motor should give you a degree of freedom, right? You want to do a 2-DOF or a planar robot, you need at least 2 motors. So a Stewart platform is a platform that has 6 motors, so you have 6 degrees of freedom. So Stewart platforms, you can either use a rotary motor or a linear actuator to actuate those lengths, and they're aligned or configured in such a way where you get the 6 degrees of freedom. So none of the joints are redundant. So redundant means that the motors are running the same axis. So why do we need a Stewart platform? Or why? So Stewart platform, like I said, has 6 degrees of freedom. So if you need to basically make a platform that complies, you can do that. If you want to make a game, like an airplane game, you might be able to use a Stewart platform. So now I'm going to get into the mathematics behind a Stewart platform. You can see here we have our x, y, z coordinate in 3D space. So our green is our z, our red is our x, and our blue is our y. So as you can see now we rotated our frame as you can see, so we'll call that theta psi. So this is our rotation matrix along the z-axis. So our first element is cosine psi, which is x contribution of x. So meaning that red frame way in the bottom rotated, what portion of x is contributed to that rotation? So in this case is cosine psi, and the next element is sine psi, which is the y contribution to x. And the last element is 0, because that's z's contribution to x, which is no contribution. And then our next row down, so notice that sign negative because the contribution is in the negative direction. And then for our y contribution of y is going to be cosine because it's in the positive direction. And again, z has no contribution to z. This is our frames. So if you do the calculations, you should get this. So now multiplying them all together, we get this giant matrix. And this is going to be what we're going to use for our inverse kinematics. So we're going to be using these particular equations. So these are the x and y contributions. So this is the SolidWorks model that I drafted. So first things first is that we need to find out these particular points relative to the entire frame. So in this case, I made these servos equally spaced. So basically from here to here would be 60 degrees. And you find that radius to get that point. So you have 6 points that are stationary on top, and you have 6 points on the bottom that are actively moving. But the relative 6 points on top are relatively easy to solve. Just find that radius distance and also that theta angle, and you'll be able to figure out that particular point in 3D space. for finding this point, the bottom point, the dynamic point, that's a little bit more involved. I'm going to go more into detail talking about rotational frames and how to manipulate the numbers. So as you can see from the picture, that by moving these two angles, by moving these joints, we're able to manipulate the bottom platform to do whatever we want. And we can see from the top that I have everything. I can know exactly what kind of angle, so I can double check my work. So this one, so if I go to 90, okay. So next thing, after we figure out these points, and using our inverse kinematics, we can figure out these points right there. So basically we're finding this point, we're finding that point to this point right there, and that is the length that we found using our inverse kinematics. So now what we need to do is we need to back calculate those angles, right? From here to here, we have this serval horn length right there, and we have this length here, and from our triangle law of cosine, we can figure out that length right there. So I'm going to talk more about this in code. So first things first, we closed everything. We have our servo, and then we attached our Arduino. These are just declarations. Our connecting rod, our radius from our middle point to our point of pivot, servo horn, and that tiny little distance from the servo horn to that tie rod. There's screws, there's a screw, so there's an offset. So these are our thetas. So in this case, our stationary one is 60 degrees apart from each other, and then for our dynamic one, these are those angles that I found from SolidWorks. To calculate that point, those 6 stationary points, we basically figure out our radius and our theta, and then we can figure out our x and y coordinates. So now this is our dynamic, so our bottom platform, we figure out that radius. This is a dynamic home is basically our offset. So we have our XYZ translation. So these are the parameters that we're actually going to change. So this one is our X, Y, and Z for our rotation. So we actually have 6 degrees of freedom. This massive equations right here is basically the equations that we looked at, our giant matrix, and then those are the ones that are circled or squared with that red box. So now that we know our points from our 6 stationary points and also our 6 dynamic points, we can figure it out using our Pythagorean theorem to figure out those lengths based on those 2 points in 3D space. So this is basically a Pythagorean theorem to get that tiny length offset, so to get it more accurate. So now once we have this, we can use our law of cosine right here to solve for those angles. And then after we solve for those angles, we basically can print out those angles. And so that's basically all the inverse kinematics that we can, all the inverse kinematics. You can write, you don't have to use MATLAB for this. You can use Arduino. So this is actually the GUI for MATLAB. So basically, opened a figure, plotted X, Y, and Z, made my axis, and then I plotted those points and connected those lines with this. And that's the whole code. If you liked the video, like it. And if you haven't subscribed, please. And thanks for watching.